Hello everyone. Today we are going to build a fully functional web server that returns some JSON data written entirely in x86-64 assembly language. I know that you are thinking, assembly? Isn't that super complicated? Well, yes and no. By the end of this tutorial, you will understand exactly how web servers work at the lowest level possible. So, what exactly we will build today? We will build a minimal HTTP server that listens on some port and it will return some JSON response, and it will be built entirely using Linux system calls. That means we will not use any external libraries. And in this tutorial, we will learn how sockets work at the system level, then how HTTP responses are structured, and also the logics behind the network programmings. Now let's get a conceptual overview of our today's project. Here I have written a pseudocode so that you can understand better. So first of all, let's say we will have a main function. Then we need to create a server socket. It will be used to communicate with the client. So we will create the server socket by calling the kernel service for creating socket. Then we have to pass some arguments. First of all, AFINet, that is the address family for IPv4. So this tells the operating system that I want to communicate using IPv4 addresses. Then we will have to pass socket stream. It is like the protocol, that is TCP or UDP. Then we have to pass 0, that tells the kernel to use the default protocol. After that, we'll have to create structure for the address or API, that is the IP and the port. So here we'll pass the family as the AFINet, that is the IPv4. We have selected the port as 8080 and we have to pass the address, that is the localhost one. Then we need to bind the server socket to the address. So we will call the bind system call. Then we will have to pass some arguments here. First of all, the server socket that we just created. Then a memory pointer to address. Then we will have to pass the size of address. Now we will listen for connections. So listen server socket, and we have passed here 5. That means there can be up to 5 connections wait in the queue. Now our server needs to be continuously accepting connections, so we need to run an infinite loop. For that reason, we have written while 1. And first of all, here we will have to create the client socket using the accept system call, where we need to pass the server socket, then null and null, because we don't need any other info about the client. And then we will send the responses. We'll write the response headers. So for that reason, first of all, we have done the write system call and passed the HTTP version and the status code. Then we have passed the content type, that is for our case application/JSON. And then we have passed the content length, and this length is the length of this JSON message. And then we have closed the connection. And as it is running inside the loop, it will not be closed after the first connection. It will again start running and start accepting further requests. Now let us see some basic commands of x86-64 assembly. So here, unlike all the programming languages, all the operations are done through registers. There are almost 16 registers and each register is 64-bit. That's why it's called x86-64. If we wanted to do addition in normal programming languages, then we stored some data in a variable. But in case of assembly, we need to store it in a register. So we store it by this move command. Also, we can copy the value of one register into another register. We can add 2 values by add command. Then there comes system calls. System call is like you are asking the operating system to do something for you. In Linux, you do this by syscall instruction. So put a special number in RAX register, and there are a bunch of system calls. Like if you want to create a socket, if you want to write something, if you want to read something, for all these operations there are system calls. So for doing a system call, we need to pass that unique number for that definite system call in RAX register and just write syscall. So the operating system or the kernel will do it for you. And there are generally 2 sections. One is data section, another is code section. Code section also known as text section. And the underscore start, that defines the start of any program, and all the data that we need for our program are stored in the .data section. Now what are the prerequisites and requirements for this project? First of all, you will need a Linux machine. I am using WSL, that is Windows Subsystem for Linux. You can use your own Linux machine or virtual machine, and if you are using Windows like me, you can install WSL from Microsoft Store. Just go to Microsoft Store and search for Ubuntu, and you can install any version from here. Then we will need an assembler to assemble our codes, that is the NASM or network assembler, and finally a GNU linker that we will use is LD. Now let us install the assembler. So sudo install NASM. So you can see I have already the newest version. Now I will just install the binary utils. So sudo apt install, and I also have the binary utils as the newest version. So I can now get started with building our server. Firstly, I will create a folder, my server. Now let's open it using VS Code. Now let us create a file named server.asm, and here we will write all our codes. Now let us start with the data section. So let's define section.data. Firstly, we will prepare our JSON response. So let's say JSON body. We'll define byte, then we'll create the message that we'll send. So message, let's say hello from assembly, then comma and 0. After that, we need to calculate the length of the JSON. So JSON length, that will be equal to the current position in the memory minus JSON body and -1. Why this -1? This is to subtract the null terminator. Now let us create the HTTP response headers. So response define byte, HTTP slash the version, then the status code, and okay, then 13 comma 10. This is for the CRLF, that is carriage return and line feed. They actually performs this thing /r/n. Then let's define the content type. Content type, that will be application /JSON, again the CRLF, then the content length, and here keep it empty. Now let us create the response length. So response length, that will be equal to the current memory pointer minus response. Now we will set the content length. So content length defined byte, that will be equal to the length of this JSON content. So let's count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34. So it will be 34. Then we will have to pass two CRLFs. So 13, 10, 13, 10. Then the length of this content length, that will be content length that will be equal to the current memory pointer minus content length. Now let us create the socket address structure as you saw in the pseudocode, like this. So address, it will be a total of 16 bytes. First of all, we'll define a word and we'll assign 2 here. This 2 tells the kernel that we will be using the AF inet. that is the IPv4. Then we'll define another word, and here we have to pass the port, that is 8080. But we cannot directly assign the decimal here, rather we need to firstly convert this into hexadecimal. So let's convert it into hexadecimal. So decimal to hex, 8080. So it will be 1F90. So 0 cross 1F90. And why this 0 and cross? Because it tells the kernel that this is in hexadecimal format. Now we need to pass the address. So we'll define a double word, because an IP address is 32 bits, that is 4 bytes. So a double word is actually 4 bytes. So let us convert the IP address, that is 127.0.0.1 into hex. That will be hex of 127 will be 1F, and for 0 it will be 00 dot, and hex of 1 is 01. So we can write 0 cross 1F000001, but it will be wrong, because the x86 kernel it's actually Little Indian for 32-bit words, and our IP address is 32 bits. So the NASM assembler stores the least significant byte first. So if we write this in this format, this is known as the big endian format, it will be read as Little Indian by the kernel. So for that reason we will reverse this. So rather write 01000007F. So now the kernel can write this in right order. And if you look here, you can see we have defined one word here, one word here. That means 2 plus 2, 4 bytes, and a double word here, that is 4 bytes. So total 8 bytes. But the kernel wants to receive a 16-byte address. So for that reason, we want to pad this. So let us pad it with 0. So now it will pad the address with zeros. Now let us create the runtime storage for the client file descriptor. So that will be in the .bss section, and for the client file descriptor we will reserve a quad word, so resq1. So we will use this to remember which client we are talking to. Each connection gets a unique file descriptor number from the operating system. And why we are not initializing it? Because we actually don't know the value until the runtime when accept returns it. So the BSS section is actually for the variables that we will use during the runtime. Now let us define the text section where all our code will be there, and also a global start to tell the assembler that our program starts from here, and finally our main function, that is start. That means our code starts from here. So here global start, this actually makes the start visible to the linker. The linker needs to know where the program begins. And this start, this is a label that marks where program execution begins. So now let us start our program with creating the socket as we saw in the pseudocode. So first of all, we will create the socket. So for creating socket, we need to do a system call. And we do system calls by passing a specific number into a specific register. So let's say if we pass 41 inside RAX register, then the kernel will know that I want to create a socket, because 41 system call is reserved for creating a socket. Now we need to pass some arguments here. And also for passing arguments in x86-64, there are some conventions, like the first argument go in the RDI register, the second argument go inside the RSI register, and the third argument go in the RDX register. So as we saw in the pseudocode, that first of all we will have to pass the AF inet, and for AF inet we will simply move 2 inside the RDI register. So RDI register is the first argument, and this 2 defines we will use AF inet. Then the second argument that goes inside RSI register, and here we will pass 1. This defines the socket stream, that is TCP. Then the third argument, that is the protocol. So the third argument goes inside RDX, and the protocol we set as 0 or the default protocol. But rather than moving 0 inside RDX, we can do another thing, that is XOR RDX. We know that if we do XOR something with itself, then the result is always 0. But why XOR instead of moving 0 inside RDX? Because XOR is faster and the machine code is smaller, and this is the traditional way to actually zero the registers in assembly. And when all the instructions are ready, we'll hand the control to the kernel. So simply write syscall. So this hands over the control to kernel. And finally, the result will be stored in RAX, but we'll need RAX later again for some other functions. For that reason, we will store it in some other registers. So we'll move RAX inside R12. So the server socket file descriptor will be stored inside R12. So if RAX is overwritten by any other functions, then we don't need to worry about that. Now the next job is to bind the socket to the address, as we saw in the pseudocode. So number 2, we will bind the socket to address. So here, first of all, we saw that we have to pass the server socket file descriptor to the bind function. So move RDI R12, because the server file descriptor is stored inside R12. After that, we need a pointer to address structure. So we'll load the effective address and store it in RSI. We'll load the relative address of the address structure. Then the third argument was the size of address structure. So move RDX. So the size of the address is, you saw here, that is 16, because 8 bytes here and the left 8 bytes we did a padding. So we will pass 16 here. And then the syscall for bind is RX49. So this is the syscall for bind. And finally, we'll hand the control over to kernel. Now we will have to listen for connections. So number 3, we'll have to listen for connections. So for that, the system call is move RX50. So this tells the kernel to listen for any active connections. And finally, we'll hand over the control to kernel. But this system call or the listen method, it also wants some arguments. Firstly, it will need the server socket file descriptor. Then it will need the queue size. So all the initializations are done. Now we will simply accept the connections and send our response back. So as we want to continuously accepting connections, so for that reason we will have to write a loop here. So accept loop, and finally jump to accept loop. So this is the while loop as we saw in the pseudocode. Now here, first of all, we have to accept any incoming connections. And this accept method, it took some arguments. So first of all, it took the server file descriptor, then it took null and null. Let me write the pseudocode for these functions too, so you can understand better. So this one, it is the system call for creating the socket, and it takes the AF inet as the first argument. This is the AF inet. Then the second argument, it is the socket stream, and the third argument is 0. So we pass all of them in this system call. And this is the system call for bind. The first one is the server file descriptor, and the second one was a pointer to address structure that we saw in the pseudocode, and the third one is the length of the address. Similarly, the listen system call, it takes the server file descriptor as the first argument and the size of the waiting queue. Now here, system call for accept is 13, and syscall to hand over the control to the kernel. And finally, we'll store the client file descriptor inside client fd from rx. So this one we initialized it in the .bss section, so it will be initialized during the runtime. And the arguments we have to pass here, the first argument inside RDI, that is the server file descriptor. Then the second argument inside RSI, that is 0 or null. And the third argument also null or 0. Then on the fifth step, we will send the HTTP headers. So we'll send them by simply write system call. And the system call number for write is 1. And the arguments we will send, first of all, it will need the client file descriptor as we saw in the pseudocode. And the second argument will be the pointer to our response headers. So we'll load the effective address inside RSI of response. And the third argument will be the number of bytes to send. So move rdx response length. So in RSI there will be the pointer to our response headers, that means the pointer to this, and this one tells that how many bytes after this address needs to be sent. So we have calculated the number of bytes here inside response length. So starting from here, the number of bytes equal to this response length will be sent to the client. That means this whole HTTP headers will be sent to the client. Now after that, we need to send the content length. So send the content length. So this will be similar to this one. Just copy and paste it, but here instead of response, write content length. And this was content length. That means how many bytes of the content length need to be sent after the pointer. And after that, we will send the JSON. Send JSON data. And it will be also similar to this one. So copy this and paste that here. I think we did a typo. And here instead of content length, it will be the JSON body. And here it will be JSON length. And after this, we need to close the connection. So for closing connection, the system call is number 3. And before closing, we need to pass the client file descriptor. So we'll move the client FD inside RDI. So that's all. This is all about the server. Now let us compile the code. So go to your terminal and we'll compile using NASM. Then /f, we will pass the output format, that will be elf64. So this is a 64-bit elf executable format for Linux. Then the input file, that is server.asm, and the output file will be, let's say, server.o. And run this, and we have got an error. So content length is undefined. Okay, so we did the typo here actually. So it will be GTH length. Now let us again try to assemble it. Okay, now we have got no error, and here you can see the output file. Now we just need to link this up with a GNU linker. So let us link this up. ld server dot output to, let's name it server. So this will be the executable file, and this is our output file. So we are simply linking this output to this executable. Now run enter, and you can see the executable here. Now you can run this using sudo/server, give your password, and probably the server is running. Now if you do curl verbose curl to localhost 0.0.0.1 and port 8080, So the connection is refused. Let us see what we did wrong here.
A few inches later.
Okay, so we have written this in the network order. That means how the network protocol reads this. That is the big Indian format. But the x86-64 CPU use the little Indian format. So I think we need to solve this. So this will be 901F. Now let us save this and close this using Ctrl C. Now let us assemble this again. And now let us link this up. Now if we do /server, now let's do the curl again. Okay, still trying to connect. There may be some errors after it connected to the server. So let us go back to the code again. Okay, here we have to do XOR actually. And the system call for accept, is it 13? Let me check. So it is 43 and we have written 13. It is actually 43. I think there is not any more bugs. Now let us again assemble it. And link it again. Now if we run the server and do a curl here. Okay, so finally we have got the data. So here you can see the JSON response that we are sending from the servers.